You are now standing inside the beam pipe of one of the largest particle accelerators on Earth. There is an immediate problem with this scenario. During actual operation, you could not safely be here. The accelerator contains powerful electromagnetic systems, intense particle beams, and radiation generated when particles interact with surrounding material. So, for the next few minutes, imagine that you are somehow completely unaffected by all of this, allowing us to follow the particles from inside the machine. The tube surrounding you is surprisingly empty. A particle accelerator does not want its beam traveling through ordinary air. Air contains enormous numbers of nitrogen, oxygen, and other molecules, and a high-energy particle passing through them would constantly collide with those molecules, losing energy and scattering away from the intended path. Instead, the inside of the beam pipe is maintained at an extremely high vacuum. There are still occasional molecules present, because producing a truly perfect vacuum is practically impossible, but compared with the atmosphere around us, the tube is extraordinarily empty. This gives the accelerated particles a relatively clear path around the machine. Now imagine that a proton enters the accelerator behind you. It begins with an ordinary speed compared with what it will eventually reach, but it is about to pass through a series of devices that repeatedly increase its energy. Despite the name, particle accelerators do not usually accelerate particles by mechanically pushing them, they use electric fields. A proton carries a positive electric charge. Place that proton inside an electric field, and the field produces a force on it. Arrange the electric field in the correct direction, and the proton gains speed and energy. Modern accelerators commonly use structures called radio frequency cavities, or RF cavities. Inside these cavities, electromagnetic fields oscillate extremely rapidly. The timing is adjusted so that a bunch of particles arrives when the electric field is pointing in the direction that accelerates them. The particles receive a push, then they travel toward another cavity. They receive another push. This process happens again and again. The beam is not normally one perfectly continuous line of particles. Instead, the protons are organized into bunches. Each bunch contains an enormous number of individual particles traveling together through the accelerator. From your imaginary position inside the tube, these bunches would repeatedly pass through the same sections of the machine as they travel around the accelerator ring. At first, each acceleration stage noticeably increases their speed. But something strange happens as the protons become faster. According to special relativity, no particle with mass can be accelerated beyond the speed of light in a vacuum. The closer the proton gets to that limit, the harder it becomes to produce another noticeable increase in speed. Eventually, the proton is traveling at more than 99.99999% of the speed of light. Adding more energy barely changes its speed anymore. Instead, the additional energy increasingly appears as relativistic energy and momentum. Please consider subscribing if you're enjoying the video so far. I'll be uploading many interesting videos regarding physics, tech, and chemistry. This means that saying a particle accelerator simply makes particles faster and faster becomes slightly misleading at the highest energies. The speed approaches the speed of light without reaching it. The energy, however, can continue increasing enormously. A proton in a powerful accelerator therefore carries far more energy than an ordinary proton moving through everyday matter, even though its speed may differ from the speed of light by only a tiny fraction. But now another problem appears. The accelerator is curved. A particle moving rapidly through space naturally wants to continue in a straight line. If nothing acted on the proton, it would leave the circular accelerator almost immediately. This is where the enormous magnets surrounding the beam pipe become essential. Because a proton has electric charge, a magnetic field can change the direction of its motion. Large dipole magnets are positioned around the accelerator to bend the beam gradually around the ring. The particles repeatedly attempt to continue straight ahead while the magnetic field continuously redirects them. At a machine such as the Large Hadron Collider, this process requires extremely powerful superconducting magnets. Superconductors are materials that, under the correct conditions, can carry electrical current with essentially no ordinary electrical resistance. This allows enormous currents to create powerful magnetic fields without producing the same resistive heating that would appear in an ordinary conductor. But achieving superconductivity requires extreme cooling. The main LHC magnets operate at temperatures only a few degrees above absolute zero. So while the proton beam carries enormous energy through the middle of the accelerator, parts of the surrounding machine are simultaneously colder than most of outer space. Not every magnet bends the particles around the ring. Some magnets focus the beam. Even if billions of protons begin traveling in roughly the same direction, tiny differences in their positions and motion would cause the bunch to spread out over time. If that happened, particles would eventually strike the walls instead of reaching their intended destination. Quadrupole magnets act somewhat like lenses for charged particles. They focus the beam in one direction, while behaving differently in the perpendicular direction. By arranging multiple magnets in sequence, engineers can keep the particle bunches tightly controlled. The accelerator therefore becomes a gigantic optical system, but instead of focusing visible light with glass lenses, it focuses charged particles using magnetic fields. Now imagine looking down the beam pipe. One proton beam is traveling around the accelerator in one direction. In machines designed for particle collisions, another beam can travel around in the opposite direction. Most of the time, these beams are deliberately kept apart. At a few carefully selected locations, however, powerful magnets focus both beams until they cross. This is where the accelerator changes from a machine for accelerating particles into a machine for studying them. The objective is collision. Two proton bunches approach each other at almost the speed of light. Each individual proton is tiny compared with the space between the particles inside the bunches, so most protons simply pass through without directly colliding. But because there are so many particles and the beams cross repeatedly, some protons eventually interact. When two high-energy protons collide, they do not behave like two microscopic billiard balls smashing together. A proton is not fundamental. It contains smaller particles called quarks, held together by particles called gluons. At high enough collision energies, interactions can occur between these internal components. The energy concentrated into the collision can then produce completely new particles. This is one of the most important ideas in particle physics. Energy can become mass. Einstein's equation, E equals mc squared, works in both directions. Mass can be converted into other forms of energy, but sufficiently concentrated energy can also produce massive particles as long as the relevant conservation laws are obeyed. The collision therefore creates a brief collection of particles, many of which may exist for only an extremely short time before transforming into other particles. Scientists cannot simply look through a window and watch this happen. The important particles are far too small, and many disappear almost immediately. Instead, the entire collision point is surrounded by an enormous detector. A modern particle detector is built in layers. Different particles interact with matter in different ways, so each layer is designed to reveal a different part of what happened. The innermost detectors track electrically charged particles. As a charged particle passes through sensitive material, it leaves small signals at different positions. Combine enough of those positions and a computer can reconstruct the particle's path. Because the detector contains a magnetic field, charged particles follow curved trajectories. How strongly the path curves provides information about the particle's momentum. The direction of the curve can also reveal whether its electric charge is positive or negative. So from a series of tiny measurements, physicists can reconstruct something that was never directly photographed. Outside the tracking system are devices called calorimeters. Their purpose is to measure energy. Particles enter the material and interact repeatedly, producing cascades of secondary particles. By measuring the resulting energy deposited throughout the detector, scientists can estimate how much energy the original particle carried. Different calorimeter sections are designed for different categories of particles. Outside these are additional detector systems, including layers designed to identify particles such as muons, which can pass through much more material than many of the particles produced in the center. The final result of one collision can therefore look less like a photograph, and more like a complicated explosion of lines and energy deposits extending outward from one central point. Computers analyze these patterns and attempt to reconstruct which particles existed immediately after the collision. One event might contain particles that physicists have already observed millions of times. Another might contain the signature of a rare process. The challenge is that particle accelerators can generate enormous numbers of collisions. Scientists cannot save every measurement produced by every detector indefinitely. Instead, specialized electronics examine events extremely quickly. Trigger systems decide which collisions appear interesting enough to keep for further analysis. Events that match certain characteristics are recorded, while huge quantities of less useful information can be discarded. Even after this filtering, researchers may collect enormous datasets. A rare particle might appear in only a tiny fraction of collisions, buried among vast numbers of ordinary events. Finding it becomes a statistical problem. This is essentially how particles such as the Higgs boson can be discovered. A Higgs boson does not remain inside the detector waiting to be collected. It exists for an incredibly short time and transforms into other particles. Researchers instead search for the combinations of particles that its decay is predicted to produce. Imagine repeatedly reconstructing the energies and momenta of collision products. Most combinations produce an irregular background. But if an unstable particle with a particular mass is being produced, certain combinations can begin forming a statistical concentration around that mass. Scientists are reconstructing an invisible particle from the debris it left behind. Now move away from the collision point and return to the beam itself. A circulating beam contains a large amount of stored energy. Because of this, the particles cannot simply be allowed to hit random parts of the accelerator when an experiment finishes. A powerful beam striking sensitive equipment could damage the machine. Accelerators therefore contain beam dump systems. When the beam needs to be removed, fast magnets redirect it away from its normal orbit and into a specially designed material capable of absorbing its energy in a controlled way. Even stopping the particles requires its own engineered system. This also explains why you could never actually experience the point of view we have been imagining. A particle accelerator is not a giant empty tunnel that happens to contain a few invisible protons. During operation, the accelerator environment includes intense beams, powerful magnetic systems, cryogenic equipment, high voltages, and radiation produced by particle interactions. Access to relevant areas is tightly controlled, and the machine is designed so people are not present where operating beams could expose them. The beam pipe itself is also far too small for a person in the first place. Our journey has really been an enormous change in scale. We have shrunk ourselves down enough to travel beside particles only around a quadrillionth of a meter across. From that perspective, a particle accelerator becomes easier to understand. First, particles enter an almost empty vacuum. Electric fields repeatedly give them energy. Magnetic fields bend and focus them. As their energy rises, relativity prevents their speed from ever reaching or passing the speed of light. Opposing beams are guided toward carefully controlled collision points. The collisions transform concentrated energy into showers of particles. Layers of detectors measure their paths and energy, and computers reconstruct what happened from the signals left behind. The strange part is that the enormous machine exists to study objects unimaginably smaller than itself. The Large Hadron Collider stretches for roughly 27 kilometers around its ring, yet the interactions it studies happen at scales smaller than an atomic nucleus. Thousands of tons of magnets, detectors, cooling equipment, electronics, and shielding are required because individual particles are so difficult to control and observe. A particle accelerator is therefore less like a giant microscope in the traditional sense, and more like a machine for deliberately creating microscopic events and reconstructing them afterward. If you could actually travel alongside one proton, almost nothing about the machine would resemble the dramatic collisions shown in diagrams. For nearly the entire journey, the proton would simply move through an incredibly empty tube, while invisible electric and magnetic fields manipulated its motion. The spectacular part lasts for an almost unimaginably short instant. Two particles interact. Energy is redistributed, new particles appear, some disappear almost immediately, and the detector spends far longer recording the consequences than the collision itself ever existed. That is what being inside a particle accelerator would really mean. You would be standing inside one of the emptiest environments humans can manufacture, surrounded by some of the largest scientific machines ever constructed, watching particles travel almost as fast as the laws of physics allow. And all of that machinery exists to understand what happens during a collision smaller and shorter than anything human senses could ever observe directly.